So first of all, welcome. It's great to see so many new faces. We've got a cozy group today, but that can be used to your advantage because now I think it might be easier for some of us to meet other people. Sometimes in a crowd, it can be a little overwhelming. So take this opportunity to see who's hiring, or maybe you have a position or some leads that you can share. I know that we've got some job seekers in the group today. Cool. A couple of housekeeping things. Code of conduct. You can find it on our website, DenverScript.com. But I'll give a brief overview. So DenverScript is dedicated to providing a harassment-free community for everyone. If anyone violates these rules, they may be sanctioned or expelled from the community at the discretion of the organizers. And if you're being harassed, notice that someone else is being harassed, or have any other concerns, contact an organizer or send us like a note on the website. There's multiple ways. We've got organizer CJ and organizer Marlena, and Chad is not here tonight, Cheddar, but he's around in the future. So bug any of us. We want to help, and we want to make sure that the community stays vibrant. So some ground rules for tonight's event. First of all, we just ask that you be kind. Please don't talk over the organizers or the speakers. Like when we're up here doing stuff, obviously things will happen when we're networking, and that's just how networking goes. During the Q&A though, we will ask that you ask constructive questions, and please avoid gotchas or questions that try to prove a point. All of the speakers work really hard to present and to prepare, so let's keep questions, keeping the flow going instead of stopping the flow. We are live, and I'm going to look directly at the camera to say that if there are any regulars out there watching the live stream, why aren't you here? Okay, but if you ever find yourself feeling a little under the weather and you don't want to miss DenverScript, find us on on YouTube. We are on YouTube. We stream almost every single meetup. So one note to keep in mind is that during the Q&A, one of us will be running around with the spatula of speaking. We're going to ask that you ask your question into there because there's people online who want to hear your question. Cool. We've got a few sponsors. Obviously, Code Talent. They are providing this wonderful space and the drinks. They are a technical talent agency. If you are looking for a gig, or if you've got a gig that you need filled, reach out to them. There are some business cards floating around in the general space, or look them up online. I like to give the long-running joke of they are recruiters that know the difference between Java and JavaScript. And then food tonight is provided by Marlena. If you want to throw a couple dollars Marlena's way, this is the Venmo, and if you would like to take a picture of it, please do, but it will also be on YouTube. Cool. All right. We are always looking for sponsors. If your company or you would like to sponsor, email us at DenverScript@gmail.com. Food is not that expensive for a meetup this size. Sometimes it gets a little much, but your company can probably happily cover it to get the exposure. So just keep it in mind. We are also always looking for speakers. Even if we do get a ton of speakers, they might not always have the schedule that works with DenverScript, or they might be on vacation at DenverScript's next event or something. So if you've got something inside that you'd like to talk about, please do. It can be JavaScript related, and you do not have to be an expert. If you're not feeling comfortable being up here giving a full-length talk, we've got lightning talk spots. All of the organizers are experienced in speaking at conferences and meetups, so if you would like someone to talk you through it, help you prepare, help you practice, reach out. One of us would love to help you get started on your speaking journey. Next up is JS News. I'm delivering the news, so I won't hand it off like I normally do. For those of you who are familiar with how this goes, I'm going to do this really quickly because y'all can Google the news if you want. And I want us to get to the speaker and extra networking tonight. So a couple of things I'll call out. Roll down Vite is going to be just like a drop it in. Eventually, it will be replacing the current bundler. Cool. You should take the State of CSS survey. This is not JavaScript, but y'all probably write CSS. or work with it in some way. So feel free to take that. And then something to keep in mind is that there are always proposals coming through at TC 39. So there's a couple that are like ready to go. They're at stage 4, so we're going to be seeing them in action pretty soon. Find them right there, but I encourage you to Google them, read about them, see if it's something you want to use, because they're in there for a reason. Let's see. A couple of resources and articles. For those of you who have seen me do the news, you know I'm pretty light on these. A couple that looked interesting is Svelte Summit uploaded all of their recordings to YouTube. So if you're interested in Svelte, watch those. You might be curious how imports work in React Server components. Check that out. And then something to kind of always keep in mind with everything is end of life for various versions, particularly Node in this case. I am a huge proponent of community and trying to get y'all out there into the world. So I'm going to take some time to call out some conferences that are coming up. UberConf, it's in Denver. It's next month. Check it out. I don't know the prices, but if you are like hurting and you don't think you could afford a ticket right now, or your company won't purchase a ticket for you, reach out, see if they need a volunteer. It's a really good way to meet some people, network, and then maybe see a few of the talks for free. Grand Rapids has a conference coming up, Beer City Code. I love the name. Utah JS, not too far. That could be a good one to check out. SquiggleConf, Cascadia. There's a conference in New York coming up. Dev2 Next, Smashing Conf, all things open, and then React Summit US coming up in New York as well. Are there any other conferences or meetups coming up in the Colorado area that y'all know of? Yes. Oh. July 29th, for those of you who no longer like JavaScript, go to Laracon. You might see a couple of us there. So, cool. Awesome. Any others? Yes.
Where can they find all these links?
Ooh, yes, thank you. If you are interested in finding these links because you don't want to have to Google them, go to DenverScript.com. We've got a whole section of news. It's all there. Let's see. Yeah, okay. I'm all zoomed out, but you can find it up here. Cool. And then lastly, we've got some releases. I'm not going to go through these, but if you're interested, write them down, Google them later. There's always releases, so I don't like to dig into them too much unless it's like something huge. I will say that the biome one has been gaining a lot of press, so maybe check that out. Cool. With that, I will ask the audience any news that you would like to share regarding the JavaScript world or the Denver JavaScript community. Cool. Quiet out there. All right. Well, with that, I would like to give us all a couple minutes to grab things that we need. Maybe you need a drink, maybe you need a sandwich, but in what, 3 minutes, 5 minutes? 2 minutes, Nick is gonna kick us off with an amazing talk, digging into some like under the hood stuff of the event loop. Awesome, I'll release you for a couple of minutes. See you in a bit. All right. Oh gosh, that's really loud. Sorry. Hey y'all. Super loud. All right. I'm going to draw everyone's attention back to the front. Oh, sorry. Music has to go down. We're still grooving. All right. All right. Thank you all. We're going to dig into the content. I want to introduce Nick for the talk Get Low, Getting Underneath the JS Event Loop. I'll hand it over with a round of applause, please.
Thanks, guys. Okay, there we go. Thanks, Cass. Appreciate that. Yeah, so my talk is about the ability to get underneath the JavaScript event loop using WASM, or WebAssembly. A little bit about me. My name is Nick, and I kind of came up through the ranks of programming from C++ all the way through Python, Java, C#, JavaScript, Perl, you name it. So I've worked in a lot of different industries, including finance, video games, healthcare, and several others. And I'm awful at PowerPoint and Excel. So if this presentation is terrible, it's completely my fault. I never learned how to use business analytics tools. So these are kind of 3 samples of some of the work that I've done. On the left is a video game that was released in Asia. In the middle is actually one of the first interactive charting financial applications built in the original Android NDK. If anybody remembers writing in Kotlin, that's amazing. But this actually was the front end that used the back end that is the basis of this talk, actually. And then on the right side is a financial streaming system, a SaaS platform that is basically built by the same company. So I built the streaming system for all the feed data for Japan, which runs that. And again, that is actually the core and real-life example of basically this talk. So quick question, quick show of hands. How many of you guys actually know something about how the event loop works? Cool, yep. And how many of you have used WebAssembly or are familiar with it? All right, cool. So let's go over what this talk is about. That's kind of what I expected, so not a lot of people kind of really know about that stuff, and that's fine. This talk is a little bit more advanced. It's not really a vibe coding thing. It's really trying to get to some more of the core concepts of how JavaScript works. But I'm going to try and keep it as informational and light as possible, so I'm not going to try and hammer you with like C++ or anything like that. So anyway, what is this talk really about? It's about a real-world use case where we need to work around JavaScript, specifically, the event loop. A little bit of history of JavaScript itself and kind of why we have invented WebAssembly and what's going on there. Shedding some light on WASM and some other advanced topics. And just, it's another tool in your toolbox, right? If you get stuck in a situation where you don't know what else to do and you need to figure out a way to optimize, hey, you got another tool. Now, what is this talk not? What this talk isn't? This is not an argument for C++ over JavaScript or TypeScript, that if you want to have that conversation, please go online. There are plenty of subreddits you can argue all day with people about. It is not a definitive authority on how to write hyper-efficient code. I will openly admit there's many more optimizations and the code is generally not great, but it is open to you guys. I have the link at the end. So it's not trying to tell you how to write the most efficient code. And it's not an attempt to get you to prefer WebAssembly over vanilla JS, right? This is not me pushing doing things in another language just to get JavaScript to work. JavaScript, as we're going to see, has a lot of great features, and as you guys know, is constantly evolving and iterating to become more and more powerful. There's no reason for you to favor going to WASM first. This is just, again, if you kind of come up with a situation where you need to think a little bit outside the box, here's one outside the box technique. So let's talk about a real world situation. As I said, a couple of samples in the photos. The Tokyo Stock Exchange, the Osaka Stock Exchange, JASDEC, which is the Japanese equivalent of NASDAQ, they send over 1 billion stock tickers every single day. Right? Now that's on average. If you're talking about a situation like several years ago when the airline JAL crashed, it went bankrupt, the entire stock dropped to 1 yen. That's less than 1 penny. you can imagine that we had a lot more. I think it was about 8 billion. These streams, obviously, you can't really put them down one pipe. So they broadcast them over about 10 to 20 different channels and systems. You can have something like 4 different platforms, each with 10 different streams, and depending on how you subscribe, that gets further and further. And so you end up with sometimes up to 100, 120 different streams of data coming in at a massively fast rate. And each exchange has their own format, right? JazzDeck is based on the NASDAQ format. Tokyo is based on the NYSE. Osaka has their own proprietary thing that they built with, I think, Intel or IBM. And that's probably changed at this point. But essentially, they all have their own different way of doing things, and you need to kind of figure out a way to get that all together, right? You want to try and unify that as much as you can. But we need it to be high speed and low latency, right? If you're talking about a stock ticker that's got a delay and the price changes in the time that you put in either a purchase order or a sell order, you can imagine you're going to lose a lot of money, right? So we need it to be as fast and low latency as possible. But mistakes can happen, right? In programming, human error, we need some way that we can very quickly manipulate the business logic, right? So there's some things that we need some flexibility to. How can you make a system that is very fast in both data service, but extremely flexible in the domain layer, right? And that's the question that had kind of come across my desk years ago. So for this talk, we're going to do a proof of concept of this. The idea here is to create an application that takes in multiple data feeds as input and measures market volatility, right? The main loop, right, is basically your rendering loop. It's going to present the volatility at a regular interval. For those of you who are familiar with things like React, this is where your components are actually being rendered, right? You're on your main thread, it all gets compiled out, and bam, it's going to render this. Now, the ticker data has a fixed format. Again, this is a proof of concept. Basically, each ticker starts with a character code. It's got the file name. It's got either P or V to indicate price or volume. The value. So if in this case, if it's a price, it's a float. It's a decimal. If it's a volume, it's a long. So we don't know that until we actually check whether it's a P or a V. And then the timestamp of when it actually was created in milliseconds. And it closes with X03. It's just a character code that exists in the ASCII table. It just means, hey, that's the end. And the goal is to present the volatility as quickly and stably as possible. So how are we going to actually measure the volatility? We're going to use something called Euclidean distance. So for every 10 packets that we get, every 10 tickers that we get, we're going to calculate the price and the volume pair, the distance of the past n number of tickers that came through. And I think in my case, I'm doing about 1 million. So I'm looking at any given time, or at every 10 packets or so, I'm looking at the last 1 million tickers and saying, what's the average distance of the price and volume now compared to that, right? So Euclid needs 2 points. It needs a P1, which is the price of the first item, the volume of the first one. And then it needs a second point, price 2, volume 2. And the distance is square root of P2 minus P1 squared plus V2 minus V1 squared. A little bit of math. There's going to be a quiz later, but even if you fail, it's fine. The only reason I bring this up is so that you can understand conceptually what we're doing. Essentially what I'm trying to do is do what's considered a very, not complicated, but heavy mathematical calculation over a lot of data, right? In the low-level computing world, square root is kind of like one of the worst things you could call. It's really expensive. No one wants you to do it. There's all sorts of things that they do to get around it. But in this case, we can't optimize away because we don't have fixed values, right? It's going to be coming streaming as fast as possible. So the greater the distance, the higher volatility means something big is happening. That's what we're trying to present to the screen as fast as possible. And what we're going to do is we're going to make a general architecture. Both the JavaScript version and the WASM version are generally going to follow the same exact architecture for a few different reasons. One, parity, right? If I have a completely different architecture than the other, this talk is, you can kind of rip through it and say, hey, you didn't really test the right conditions. There's no constants. But also, we're going to look at this a little bit more in depth. The way that JavaScript handles data, it's better if you can kind of handle chunks of data and process them, as opposed to doing things one at a time if you have a lot of data that's coming in rapidly. So the general architecture is that we've got several DAT files, and I made a mistake on the slide, but it should be file 1, 2, and 3, not file 1 all the way. They're individual data files. That's our stream. We've got essentially a component promise or a thread, in the case of C++, which is solely dedicated to reading that data and figuring out the volatility over those 10 frames or so. And they're doing it basically on their own. They don't know anything about the other promises or threads. They only know, I got my stream, I'm going to throw it, I'm going to make something, I'm putting it into this buffer. And the packet buffer is the only place where they kind of all come together, right? That's our synchronization point, right? Everything needs to put it into the buffer so that the next step, when we do a console log, we can actually read everything in that buffer. We say, hey, stop producing for a second, I'm going to take all this out, and I'm going to throw it into the console log. So that's our general architecture. Very simple. Let's see it in JavaScript. So, essentially, I've made a set of, and I'm not going to go through a lot of JavaScript code, mostly because it's very basic. I'm going to show you a little bit of emscript or WASM code, so you guys can see that. The JavaScript code is really just a bunch of promises. But we have a utility. Okay, so what are we looking at here? You can see that we've got 6 different data files. I've created a process that essentially creates those data files streaming, right? It just blasts my disk until I hit stop. Each one of those is loaded into this worker that essentially does exactly what that architecture says. We've got a promise for each one of these different data files. It's processing the data, and then it's throwing it at the main render thread so that it can actually show us this console out. And what we're actually seeing here is each one of those little ticks is a 10 millisecond delay from the previous packet that was sent from that file and the current one. Right? So in some of these cases, we're seeing almost 70 to 80 milliseconds of delay. Right? Multiply that by 6, right? Or 10 or 20. That's what we're seeing here. You can see there's a lot of variance, right? These renders are not stable. This would be the equivalent, for instance, if you're using React or you're using anything that's got a DOM, suddenly you're scrolling through things and it becomes herky and jerky, right? Your render is hiccuping. Not ideal, right? A 70 millisecond delay for anybody who's a gamer in here, you're starting to get close to, getting a headshot, right? That's the end of it. Okay, so what happened? In order for us to kind of understand what happened, we need to dive into a little bit of the history of JavaScript. So JavaScript was originally meant only for browsers. It was invented by Netscape in 1995. If anybody still knows or uses Netscape or has used it, thank you, I don't feel so old. Widespread adoption of it didn't actually happen until 2008 when Google created V8 engine. And that's kind of how Node picked up, and JavaScript became more and more a server level language and kind of took over the world. Things like parallel programming, multi-threading, what we're looking at where you've got different streams coming in, forked processes. You've probably kind of heard these in glancing, or people have kind of generally talked about them. But once you start sort of really talking about it, it becomes really complicated really, really quickly. So these paradigms, for most people, were really complicated to grasp. Most programming languages, most paradigms we use in today are built on the concept that one thing is doing one thing at a time. CPU is doing one thing. Your computer is doing one thing. So that's not the case anymore, right? CPUs have many millions of cores, sorry, not millions, but several cores. You can execute millions of lines of code really, really quickly. Memory has gone through the roof, all sorts of stuff is happening. But how did JavaScript actually handle that? How did it keep up? So their paradigm is called an asynchronous system. So what's actually happening is that the work is actually done on one single thread. Underneath everything Everything is basically done one at a time. And asynchronous constructs like promises, callbacks, and threads allow JavaScript to essentially take chunks of work and swap them in and out. So you process things piece by piece, right? So you're not actually doing things in parallel. Even though there's a thing called threads, we're going to see in a little bit, I'll talk a little bit about why that's not actually true. And this wasn't actually introduced until 2017, right? So almost a 10-year gap before JavaScript really became popular. So what does it actually mean in the context of what we're talking about, the Node.js, or really the JS event loop? So I put Node in parentheses here because actually your browser does the exact same thing. This is kind of the way JavaScript works. Hopefully you guys can see this. If you can't, there's a wonderful post by Andrew Hu, the link's at the end. I've kind of taken this from there to explain what we're talking about, but I highly recommend you read that. He does a fantastic job explaining it. And I'm going to try and do my best to go over it kind of in general. So basically, JavaScript, when you see console log, when you write most of your JavaScript, what's happening is it's being called into the V8 engine or the call stack. And each one of your commands gets put in order onto this stack, and then it's operated on. When it needs to do something asynchronously, right, you need to do something in parallel, typically you guys call promise, or you hand something a callback. That's the two kind of most common methods. When you do that, it actually punts it over to libuv, which is a C++ level library that sits on every one of your machines, right? When you install your browser, when you install Node, it's got a version of essentially libuv installed with it. And that's what's actually taking that promise, and it's running it in the background. You can see here this database is, the I/O is happening in the background. Node and JavaScript know, hey, this is an asynchronous call. We're going to go ahead and let that deal with its own thing, and we'll deal with it when it's ready. And it goes on, it pops that off the call stack, as you can see, and it goes on processing any other commands. When that asynchronous call, that promise or that callback finishes, it comes back into JavaScript and gets put into this event queue. And this is a series of different things that have happened. You can have however many promises, how many API calls you've made, et cetera, et cetera. They all basically get put onto this queue. And as it comes into this queue, it pushes those into the call stack. So those become the new thing that Node works on. A little bit complicated to understand, but if you think of it as just units of work that are being moved around, and you can only do one piece of work at a time, that's essentially what JavaScript does. So again, what about threads and promises? Well, it depends. Okay? If you call a promise using operations, like I said, a set timeout, right? You're doing an API call, it may operate outside the main loop. Right? And that's pretty typical for the API calls, DB, queries, things like that, right? You're waiting for I/O. And a thread, again, that's a construct that essentially lets you actually run in parallel. It does technically run separately. So it is running separate from the event loop. But the moment you finish something, you got to send data back. It's asynchronous, so it has to slam everything, it has to hit the brakes, and it has to copy all that data, right? You can't just like access it. It has to basically bring it all back in, and it's super expensive. It's one of the most expensive things you can actually do is copying that data. So fundamentally, everything is still kind of executed on that main thread. Okay, but yeah, well, what happened? All right, so in the architecture that I proposed, each one of those promises is reading the data, it's buffering up a million of them, and then it calculates the Euclidean distance, right? It takes an average, does a square root, and says, hey, this is really a big spike in volume or price. But because it's a promise, instead of actually being somewhere else and waiting for a database query to finish, it jumps into the event loop and then comes right back in the main thread to process. So it's the equivalent of me putting a while true, right? Loop for 1,000,000 times. Nothing else can work. So as we increase the number of input streams, right, in this case we only needed 6, we take more and more time on that main thread. And the ability for us to actually write console log gets pushed further and further and further away because there's more stuff that has to get through. For the most part, and this isn't necessarily true, there's obviously nuance to this, JavaScript and the Node systems will just process everything in that queue, right? First come, first serve, it just blasts it out. So again, most systems, most browsers, Node does a really great job of being fair. As you could see, it wasn't like one thing, one of those promises just ran forever. It kind of knew how to, all right, give it a second and switch. Some of that it handles for you, but it's not necessarily ideal, right? As we saw, we get a lot of variance, we get a lot of deviation in what's going on. So the question again is there a way to get around it? Can we do something about the event loop? Is there something even remotely possible? WebAssembly to the rescue. WebAssembly is our solution. What is WebAssembly? Before I talk about how that statement is kind of utterly false, what is it? All right. Now, webassembly.org, a great resource to look this stuff up, says it's a binary instruction format for a stack-based virtual machine. WASM is designed as a portable compilation target for programming languages, enabling deployment on the web for client and server applications. I have no idea if any of you, I read that and I had no clue what that means, right? What does it actually mean, right? WASM gets you low, right? My definition of it, the best I can explain it, is WASM is a way to leverage certain machine level, low level components by sidestepping the typical JavaScript architecture. Now there are a billion variations of WASM and it's growing constantly. C++ is not the only one. Rust, C#, almost even Python. There are a lot of different WASM targets. It's a specification. There's a lot of different engines, a lot of different compilers that actually do this stuff for you, which is, I think, why they have a hard time defining it. But ultimately, what you're trying to do is you're trying to get access to some low-level component, something that another language does better or your system does better than your browser or Node. So here's the standard JavaScript kind of how, when you write console log, right? Or if in my case, get average distance, how does the code actually work, right? What happens to it? You write your user level code in JavaScript, send it in, it turns into bytecode, right? And that bytecode then gets optimized by the JIT. And then it turns into machine code execution. So the JIT says, okay, this is the bytecode that you need, machine, run this bytecode, right? And then it executes it and then returns the results back to JavaScript. Generally speaking, all of your code has to go through all those steps before it actually, anything happens. And the happening level is that one at the right, second to them from the bottom, machine code execution. So there's at least 3 steps above that before any of your code gets executed. If you use WASM, for instance, in this case, let's say the get average distance is actually some WASM code, it basically just prepares the data to be in a format for WASM. It shunts it down to WASM-specific machine code. So it doesn't even, it's totally different from the JavaScript one in a sense. And then it executes and returns straight back to JavaScript. So we kind of we skip almost 3 different steps of JavaScript completely. And that's kind of what lets us get around things like the event loop. So again, WASM to the rescue. We can leverage real parallelism by using something called p-threads. I'm not going to go into too much detail about p-threads, but p-threads are kind of the original bad boy thread. When you hear about threading, back in the day, it was p-threads. They are essentially what's considered, everything you talk about in parallelism and threading, that's all based on basically p-threads. So we can get right down to the p-thread level by using p-threads in parallel. We can do all the file reading and the Euclidean distance calculation basically as fast as the machine allows, right? Because I'm going to put it into a language that's as close to the machine as possible, right? That's what WASM's doing. We're going to queue all that data up, and then we're going to put it into a buffer in C++ and only move it to JavaScript when we want to render. Now that's not fundamentally different from the actual architecture. The original architecture I showed you, we did the exact same thing. The only difference really here is that instead of buffering it in JavaScript, I'm going to do it on the C++ side. And when we get a console log, I'm going to drain that buffer from WASM. So I'm paying the penalty of having to cross that really expensive boundary only once, as opposed to like doing it over and over for 10 different threads. Okay, so let's take a look. Let's look at a little bit of what's going on here. So again, I'm not going to really go through the C++ and code. I'll just say a couple things about it. The code is buildable on pretty much any machine. There are no libraries, so there's a thread manager in here. The code is not great. It's mostly because I wrote it just for this. There are packages that could have been used. This doesn't use any. So you can literally just run this. You can grab it off my GitHub, run this thing, build it on any machine. It should work without any problems. There are no dependencies. And the second reason for doing that and kind of making it simple is if I start using external libraries, this becomes a conversation about which is the best external library that can do the thing I need. That's not what this talk is about. So I'm not going to go through a lot of the code here, but you can kind of see the size of the actual packet buffer. And this is just the C++ code that gets revealed to JavaScript. You basically just write something like this. You include this header file that lets you bind the C++ code, in this case, with JavaScript. And you write these lines that essentially tell you, okay, this is the function that you're going to call in JavaScript called start, and this is the actual C++ code it's going to call. And it's as simple as that. Obviously, you can make this more complicated, but when you're starting off, you really just kind of define, hey, I want to call wait from C++ or whatever other language that you're using, and I'm going to call it wait in JavaScript. Now, I could change that to be something else in JavaScript, but again, the idea here is it's just going to do a matching. And then we run a little command, and it will build our JavaScript. So what it's doing now is it's basically just running emscripten, which is the version essentially of WASM that takes C++ and turns it into JavaScript. I've given it a bunch of commands to say, hey, compile all the C++ code. It does all that magic for you, and it produces two files. It's going to make a MJS in this case. You can also do plain old JavaScript. But it produces a JavaScript file that essentially the moment you import this or you use this, it is able to read and load all of this stuff for you, right? You don't have to write a thing. It's built all this binding code. And then it's also created a WASM file, which is binary, right? This is the actual, that kind of machine bytecode that gets matched to that JavaScript it just generated. So when it calls, it's going to go down, WASM's going to execute this thing. And then I can run this. Look at that. Minor spikes, mostly because of my machine. If I run this on my desktop back home, it doesn't spike at all. But you can see how it's stabilized, right? Again, we've got a couple times where it spikes out, but generally speaking, we've dropped down to 1 bar. That's generally speaking less than 10 milliseconds. We've completely eliminated that problem, again, for this POC. So, cool, we solved our problem. We got a proof of concept done, ship it. Magic bullet. Sorta. There are some things that are still not supported. Not all low-level operating system level commands are supported yet. You can actually code that, and here's the one pitch for C++, you can code that code to be even faster, but it won't actually work with WASM because they don't allow that specific type of code. So there are parts of certain WASM compilers that are still just pure JavaScript, right? So in this case, the file system is actually going back in a node to call the file. Ideally, that wouldn't happen, right? We would do everything. We would never talk to JavaScript. We don't have to deal with it. So the reason for that is mostly, again, a lot of these are open source. People are working on them. That hasn't been a priority. They are coming up with a new version of the file system that should solve this issue. But for now, we're stuck with that limitation in this case. Again, crossing the WebAssembly and JavaScript boundary, very expensive, right? That's where we lose so much of the time. We're copying that data. Every time you do that, JavaScript kind of has to halt. That becomes the thing it's doing, and it's just moving memory, right? Not super fast. Also, you could directly go from JavaScript to pthreads, right? There is a train of thought saying, hey, Nick, why didn't you just script the buffer and go straight into JavaScript? The unfortunate thing is that JavaScript and pthread interaction, not completely defined. So if you start using promises in JavaScript to interact with threads in your system in WASM, the system just, it goes nuts. It doesn't know what to do. It corrupts your data completely. I actually managed, I can actually do it if I increase the files count, but you can actually cause Node to panic and crash with this little code. And it's really funny because it doesn't know how to read basic files anymore. Like, it completely corrupts the data. So, just kind of a quick summary. JavaScript is powerful and easy to get started with, but it has its drawbacks. We can get around some of them using WebAssembly, but not all of them. Right? It's great for things that you know has fixed logic, reading fixed data files, doing some basic mathematical calculations that are expensive. Stuff like that, using a lower level language, using WASM, is going to do wonders if you need it. But it's not magic. It has a lot of limitations, which they're working on, and there's really not much we can do about it because ultimately what we're really doing is we're trying to shift a paradigm that JavaScript has been built on for years. Right? It's single-threaded by its initial architecture. We're trying to go around that. But the threading isn't like the only thing WASM can do. I picked that one specifically, again, because I have some background in it. And the most typical thing that people use WASM for really is the second one, graphics. There's a lot of, like if you talk about WebGL rendering, a lot of games now that are browser compatible, you actually write them and compile that stuff in WASM. That lets you access the graphics, WebGL, OpenGL ES3. But also you can use this for optimizing AI. So if you have an AI calculation that you're running using, say, TensorFlow or one of your other libraries in Python, you can't really get to run efficiently in JavaScript because it's so big. You can rewrite it in WASM and just run it at a really low level. So you can actually optimize pieces of code that, again, are fixed and you need faster. You could also use it for like image and signal processing. I don't know how many of you guys work in telemetry. A lot of like the solar panel companies these days, you're getting real-time data feed processing. You might want to figure out signal spikes. You want to do image processing. Big images will freeze your main thread, right? If it has to do calculations on each pixel and it's a 4K size, that's going to take forever. But you can do all sorts of interesting techniques if you get past JavaScript. Unit testing legacy code. There are still some places that use C++ or Perl even for doing a lot of their heavy workload. You need to make a change to that stuff. You can use things like Jest, for instance, to write your unit tests and then call into that legacy code and not really have to worry about some of those issues and like, oh, I don't know how to necessarily deal with this type of data. If you can figure out how to bind that to WASM, you can write using Jest. Module orchestration. Similar to kind of the legacy code thing, you might have a situation where you need to load different modules and use it very similar in JavaScript like you do with regular imports. It might be better for your code in C++ or C# to split it up and modularize it and then orchestrate it using JavaScript. You can kind of do that as long as you don't mind the performance hit really simply, right? Your business level code, all that stuff, and your orchestration is all done in JavaScript. And really any other places where you kind of want a hybrid approach of topological flexibility, but also performance, right? So you have a business domain where you need to make changes pretty rapidly, updating UIs, things like that, and the business needs to be flexible, but you still need some core components to be fast. That's where you can use things like WASM. So I'll open it up to questions and comments. Again, if you want to get a hold of me after this, you can scan the QR code or go to my LinkedIn. The source code is available to you. There are no tests. I apologize, there's no unit tests, but there's a README. It should run right out of the box for you. And I'd love to hear any comments if you have them. And then references, again, I highly that you look at Andrew Hu's post. He does a really good job explaining how this all works and how the kind of the V8 engine and how that stuff comes together. Way better than I can explain it. And then if you're interested in emscripten, there is the link to it.
Testing. Fascinating talk. Thank you for doing that. What questions do y'all have from the audience?
Yeah, I was curious. You brought up that usually you're doing the like 1 billion calculations, but during that stock market event, it jumped up to 8 billion.
Yeah.
Do you then change the buffer processing so that you're still rendering at the same rate, or do you just let that 8 times lag happen?
So that's a great question. So that's kind of diving a little bit more into like system architecture stuff.
Sure.
In the specific case of the actual production application, we used a lot of dedicated hardware. So this is back when SSD cards were first coming into the PCIe slot configuration, and you could get a Blade server with like several hundreds of gigabytes of memory for cheap, and we were still using physical servers. So we had we did a lot of work with the system engineers to essentially make sure that blades and servers and nodes were like right next to each other physically, and then it didn't really matter. Like we just jack up the amount of memory. On top of that, there's an architectural component. What we were actually using wasn't strictly files. Sometimes we would load the files into a DAT stream, and then we would actually broadcast it using UDP. So UDP is a protocol like TCP/IP and how HTTP works on the internet. The advantage UDP has is that I can just blast this out. It's super fast. And so what we would do is we would have a tree, a network of machines. So essentially what would happen is we would distribute the problem and just go, hey, they're so close together, we're not going to lose that many packets, and who cares, because I've got 2 different branches of it, and I've got like 5, 10 supercomputers running this thing. We're fine.
Sure, interesting.
Great question. Any others?
Yeah, my understanding of how all the JavaScript runtime stuff works is really limited. So I'm trying to think of a way to ask this without sounding stupid. So there's basically the JavaScript runtime, right? And you're communicating with WASM. Is WASM is it basically a virtual machine running in the browser?
It's not running your browser. It's running basically on the computer itself. So
it's
in the case of, say, browser development, it is the browser. So what you're actually doing is you're actually saying, don't let JavaScript figure out what I need to do with the browser. I'm saying the browser has all of these things that it can do, and I'm just going to go straight to the source. I'm going to go straight to allowing the browser to do it. So in the graphics world, which is a really easy one to talk about, WebGL, which is what you use to like render graphics on the browser, is actually part of the browser itself. And what we're doing is we're saying, okay, I'm going straight to the source. I'm going to cut all the JavaScript out, and I'm going to go and ask the browser to run that specifically.
Gotcha. So when you compile a WASM file, do you have to compile basically for every architecture you want to run on, or is it?
It's yes. Generally speaking, yes. But the advantage of what it's done for the most part is that WebAssembly code, that WASM file, if whatever it is that you're running it on is compatible with that version of WASM, so most browsers, for instance, Node, they all read that type of bytecode. So it's like basically you're building it to something that anything can read, with a couple exceptions.
I see. Okay, thanks.
Great question. All right, we've got another question.
So 2 questions. Have you, I think you mentioned something along the lines of it's expensive or it'll crash Node if you try to communicate from inside of like WASM back out to Node and back and forth. What about exposing like a shared pipe or something like that for intra-process communication?
Yeah, so that's essentially that's what this is doing here. Like when I was talking about rendering that data in C++, that's essentially creating my own pipe where I'm just loading that into data inside WASM, inside C++, and then copying that buffer just when I need it and only when I need it over. You can use more traditional pipes, you can do all that stuff as well. It's a little bit undefined. It's kind of the equivalent of whether or not you call that system level process or you do a bash command, and then hopefully the bash command works the right way and it pipes the right way. But if you run in a weird system that has a strange flavor of bash and it does something different, it's hard to say.
I heard you mention Rust also. Have you compared the Rust WASM output against C++?
I have not yet. No, not yet.
That'll be the next talk.
Yeah.
Do we have time for another question? Or okay, we've got time for one more if you're interested. I knew you were.
Two questions, actually. First one, so you mentioned earlier that you can do UDP in your C++ code that gets compiled to WASM. Do you know if you can also do like WebSocket connections or like HTTP requests?
Oh, yeah.
Okay,
Yep.
and is there a special library for that, or is it like the emscripten namespace, or?
That's a great question. So emscripten, in this case, emscripten actually has a lot of that stuff built in already. They have APIs for calling things like HTTP, and they have different things. The general paradigm is, again, to go, okay, emscripten connects you to, in this case, C++. You can use whatever C++ library in the back end. So you could just import a HTTP, library or a socket library and do it that way.
Okay.
But yeah, there's a lot of that stuff that's pre-built in. Yeah.
Okay, cool. The other question is, can we see the JavaScript code that calls those methods? So you showed us the C++ that.
Oh, sure. Yeah.
So it exposed like start, stop.
Yep.
I think it'd be cool to see how you actually call that from the JavaScript side.
Sure. So do you want to see these guys here?
Yeah, exactly. So they're
Yep.
exposed here, and then we write JavaScript code that can actually call them somehow.
So here's
Okay.
the start call,
Mm,
and then you've got the drain spikes,
cool.
and then your stop and wait.
And then reader itself is an instance. Did you have to?
Yep.
Cool. And is that something that was exposed by the compilation?
Yeah. So basically, what happens when you create this, when you write this line, or is it? Yeah. So when you create this, it'll basically automatically generate a create something module.
I see.
And so what you do is you say, all right, load that module, and then we go ahead and say, from that module, I want to call the specific thing.
Cool.
In this case, where is it? You can see the mounted paths, and then here it is, the multi-file spike reader. So it's just calling that straight on the module. It's essentially the same thing as an import.
Okay.
Yeah.
Cool.
Another great set of questions. Thank you. All right, y'all. Let's give another hand for Nick. That was awesome. Thank you so much.
Thank you, guys.